Okay, so let's explore the bisection method to find roots. So the bisection method is actually an incremental search method in which the interval is always divided in half. So if we have a function that crosses the x-axis and we search within an interval, the next search position will be halfway between, put a better color there, it's going to be halfway between the previous iteration. Okay, so the bisection method exploits a sign change near the roots. And this requires two initial guesses that obviously must bracket that root. So we could say that the root, xr, is some element of a lower bound and an upper bound in the closed interval, whereby the function value at the lower bound multiplied by the function value at the upper bound is less than 0. This is quite important, so I want you to remember this because it's going to be useful when we develop an algorithm to figure out how to increment our bisection search. So we'll also show later on that the bisection methods, the errors associated with them converge linearly. So in other words, the error at I plus 1, the next increment, is always directly proportional to the error I, previous search or current search. Okay, so how do we determine our initial guesses? Well, this is obviously quite an important starting point. And the first is we can use a graphical method. So again, if we have our function and it looks something like this, we can use a graphical method to figure out that the roots are somewhere between these points or these points. We can also use an incremental search. So what we could do is increment along the x-axis and calculate the function value for different x points, multiply them together, where you have a sign change. So fx, again, we're going to say lower bound multiplied by the upper bound. Where you have a sign change, you know you have a root. Okay, and we can also use physical reasoning. So let's use an example to explain that. If we have, for example, we could look at waves. So if we have a shore bottom with a undulating water surface because of ocean waves, let's say traveling in this direction, if we had to plot the velocity profile, it would obviously look something like this, but over time, if we had to plot it, what you would see is that as the crest of the wave moves over this point, the velocity is in this direction, and then when the trough here reaches this point, the velocity is in this direction. So let's just erase that. So if we plotted the velocity function with time, you would get a sinusoidal type function. Okay, so we could use physical reasoning here to say, okay, well, I know that a root must exist between half the period of the waves. So if this is the period of the waves, then obviously if I take the function value at the midpoint multiplied by the function value at the end or beginning of my wavelength, and I multiply these two values together, I know they're going to be negative. Okay. Okay, so let's explore the general algorithm for the bisection method. So our first point, our first step, is going to be finding or using an initial guess where we guess the lower and upper limits with the function value, the lower value multiplied by the function value at the upper point is less than 0. Okay, so that's our initial condition. Okay, then we're going to assume that the root lies somewhere between these 2 points. So our second step is going to say that the root is going to equal to the midpoint of the upper and lower bounds. So we're going to divide them by 2. Okay, now let's explore some possibilities here. The first is, so this is going to form our third step. The first is that if our function value at the lower point multiplied by our function value at the root is less than 0, then we know that this is our function, and we initially had our upper and lower point, and we take the midpoint, and we say, sorry, should be on the other side, and we say that the midpoint lies somewhere here, so that at the upper bound and the root, the multiplication of those two values, the function values, is less than 0. Then we set the upper value, so x upper value now becomes the value of the root. And we proceed with the next bisection iteration. Okay, we could also have the possibility where the function value at the lower point multiplied by the root is now greater than 0. So what does that mean? Well, if we have our function and we calculate that our midpoint is on the other side to our previous point, our previous notion, then we set the lower bound, so x lower bound becomes the root, and then we proceed again with our next iteration. Now, if we carry on and with our next iteration, and we find that the function value, the lower bound multiplied by the root value is approximately 0, we can end our algorithm, and that's our root. Let's explore some examples.